In this lecture, I want to focus on a specific loading of the fuselage, torsional loading. Torsion is a loading case that creates a twisting moment. Do you remember the vertical tail of the aircraft that was subjected to a wind load, causing torsion of the fuselage? We will now look into this load case and how it creates stresses in our structure in more detail. We can simplify the fuselage to a hollow cylindrical tube structure. Could we also visualize these stresses for the closed section? I will use this foam toy that is very flexible and has a circular cross-section. On the surface of the tube, I have drawn 4 lines around its circumference distributed equally along the length. Also, a line parallel to the axis of the tube has been drawn onto the surface. Observe what happens to these lines when subjected to an alternating twisting moment. 2 observations can be made. First, the circumferential lines rotate but do not displace or distort. Secondly, the line along the axis of the tube rotates through an angle but remains straight. By adding 2 more lines to the surface of the tube, a rectangular element can be defined. Repeating the alternating moment, the nature of this deformation becomes more apparent. As the lengths at the side of the element do not change, it can be concluded that the element does not experience any normal strains. However, the element does rotate through an angle, just as a square element subjected to pure shear would. Can we now find a relationship between a torsional deformation and the shear stress? Let's look at the graphical representation of the example I have just showed you. You see a thin-walled cylindrical tube with a radius r and thickness t subjected to a torsional moment. The rectangle shown in the initial state will deform into a parallelogram. If we take a look at just a section of this cylinder, moment m1 should be equal to moment m2 for the structure to be in equilibrium, and is equal to the applied torsional moment mt. So the torsional moment along the circumference anywhere in a structure is constant. This torsional moment causes shear stress tau and shear strain gamma. Based on Hooke's law for shear, these are related as follows. The torsional strain is equal to the shear stress divided by the shear modulus. If we can measure the strain, we can now find the shear stress. Can we also find a relationship between the shear stress and the applied torsional moment? Let's take a look at a section of the tube in a deformed state. The hollow tube has a radius r and a thickness t. We know that due to the torsional moment, there is a shear stress in the structure. This shear stress acts over a certain area, the circumference of the tube, times the thickness of the tube, and causes a torsional moment around the center of the tube with an arm length of r. We now found a relationship between the torsional moment and the shear stress. When we rewrite this, we can see that the enclosed area of the tube, pi r squared, plays an important role in this relationship. I want to introduce a new definition, the shear flow Q. It is defined as a shear stress over a distance in a thin-walled structure. For a thin-walled structure, the shear stress distribution through the thickness can be neglected and can be assumed to be constant. The shear flow is the shear stress times the thickness of the structure. For our tube, the torsional moment is equal to twice the shear flow times the enclosed area of the tube. Or, vice versa, our torsional moment causes a shear flow that is only dependent on the enclosed area A. This relationship can also be derived for other shapes of closed thin-walled structures. When the enclosed areas of the structures are equal, and an equal torsional moment is applied to the structure, then the shear flow will be the same for all these structures, independent of their shape. These closed sections are called torsion boxes, as they can resist torsional deformation efficiently. If we now want a door to step into the aircraft or a window to take a look outside while in the aircraft, you need to make a cutout in the fuselage. This cutout will disrupt the load path for shear, thus a torsion box without a cutout will not resist shear as efficiently as one without. It needs reinforcement to provide the resistance against shear deformation that was provided by the removed shell structure. We have to locally increase the thickness with doublers, stiff frames and stringers around the cutout. What we have seen today is that a torsional moment is resisted by shear stresses within a thin-walled structure. You have learned the relationships between torsional moment, shear deformation, shear stress, and shear flow. Please note that the equations we derived in this video are only applicable to closed thin-walled cross-sections due to the assumptions we made.